percent yield. Everything we've been calculating so far in stoichiometry calculations, everything we calculate is theoretical, which means it's what? It is ideal. Good. It's what's supposed to happen. Is that actually what happens in the lab? Who knows? Maybe, maybe not, right? Who knows? But everything that we calculate is considered theoretical yield. Okay? It is not actual yield, it's theoretical yield. And so when we calculate percent yield, we're looking at the ratio between our actual and our theoretical. Huh?
Is it possible to get the perfect theoretical yield in reality?
In what?
In reality.
So everything we've done so far is theoretical. Do you remember the equation for percent yield? Good. Percent yield equals actual over theoretical. Actual over theoretical. Okay? The part divided by the whole or whatever, however you're going to describe that. Then we still do need to multiply by 100 to get it into a percent, but I never write that, okay? Because I think that should be implied. If we take it actual over theoretical, we're going to put that into a percentage, okay? If we're given a percentage, you got to convert it to a decimal in order for it to sit there in our equation, okay? All right, very good. How many grams of water will be formed if 36.5 grams of oxygen are used? So I already balanced it for you. So this is going to require us to do two separate problems here. We want to find out how many grams of water are formed when 36.5 grams of oxygen are used. And then it says, what's my percent yield if only 7.95 grams are formed? We're assuming here that they're also talking about water, right? Because that's the yield we're looking for. So go ahead and run your stoichiometry calculations, and we'll see if we agree. Is that what we had for our theoretical yield? Was 10.3 grams. So now if I'm going to go in and plug in my percent yield, I'll say my percent yield is equal to my actual, 7.95, divided by my theoretical, which is 10.3. And that gives me a percent of 77.2%. Right? Because in my calculator, I'm getting 0.7718. I rounded that. The only reason I went to 10.3 here was technically because of sig figs, right? We started with 3 sig figs in our measurement. So I'm going to make my theoretical yield 3 sig figs. And so I'll round my percentage to 3 sig figs as well. Explain to me what a limiting reactant is without looking at your slide. Printouts, you little cheaters. What is it?
It's the reactant that limits the theoretical yield.
Yeah, good. Okay, good. Lots of answers there. But yeah, it's one of the reactants that's limiting the amount of production. Okay, so think of it as your ingredients, right? You run out of one ingredient. That means you can't make any more of your product. That's exactly what's happening here, right? We often at times use recipes as an examples of that. So if we've got an ingredient that we're going to run out of, it's going to limit the amount of production we can have. Okay, we don't need to go through all this then. Okay, I think we're good on mole ratios. I'm going to skip ahead. All right, what's my limiting reactant when 82 grams of copper reacts with 25 grams of sulfur? What's the maximum amount of copper sulfide that can be formed? Okay, does your slide ask you any more questions? Do I need to keep clicking through, or is it? There's some instructions, or? Yeah, okay, that's fine. But there's no other questions it's asking us?
No.
Okay, I'm going to leave it there then. Okay. Since I've got 2 starting amounts, that literally means that I'm going to have to do 2 T-charts. And in this case, I only have 1 product. So I'm going to take that to the products, right? What happens if I've got 2 products? They both need to go to the same product, okay? Sometimes you can pick, or the question might ask you about a specific product, so you would go to that one. But I'm going to go ahead and go 82 grams of copper and 25 grams of sulfur. Copper's molar mass is what, 63 and a half?
Mm.
159, is that our molar mass for that first one? Okay. What's the maximum mass of copper sulfide that can be formed? Which one is it? Is it option number 1 or option number 2? Number 1. Why is that? Because this one's bigger, right? This is maximum. But no, the truth is that we will never get to the point we'll get to make that. We have to stop production at 102, okay? Because we will run out of copper. Okay, does that make sense? Sometimes that's a tripping point. Yep. Okay. Oh, yep. And molar mass of this. So even though we are going to have less than a mole of that substance, that has a much more higher molar mass. So that's why our substance comes out with a greater mass. Okay. Let's keep moving forward then. I'm going to move into one where we do, okay, yeah, you're going to have to build and balance now. 4.95 grams of ethylene, which is C2H4, is combusted with 3.25 grams of oxygen. What's my limiting reactant? How many grams of carbon dioxide can be formed? What type of reaction is this? Good, combustion. We start with a hydrocarbon and oxygen. And what do we form as our products? H2O and CO2. Very good. Okay. And remember, what has to be true about oxygen here? It's got to be O2. O2 goes in your balanced chemical reaction. So write your reaction, but it's got to be O2 that goes with that. So I'll give you a head start, and then I'll build and balance. That way you can check before you get too far into the math. That's how I had it balanced. Does that look like what you guys had? Okay, so now let's go ahead and work the stoichiometry that goes with it. What product should I go to? What? I'm going to carbon dioxide. Why?
Literally ask how many grams of carbon
Carbon
dioxide.
dioxide. That's all right.
Well, I don't know, Brandon. Speak for yourself. I would say come back the whole time.
It's all right. No big deal. All right, here we go. Wait, you had me going to H2O now. Look what you did. Look what you made me do.
It's in the question. You gotta go to carbon dioxide.
I should go to carbon dioxide. Oh goodness. I still did it. I wrote it again. CO2. It's 44 grams. Okay. I haven't run the math yet, but I guess we'll see. It is 44 grams, right? I'm not making that up?
Yep.
Okay.
I mean, if you try.
I might be making it up, but here we go. So top one came out at, I got about 15.6. And my bottom one. Yeah,
Wait a minute.
roughly 3.
Yeah.
Okay.
Okay. I was like,
2.98 grams CO2. Yep. Because you need 3 times as many moles of O2, right? You started with almost the same amount roughly, but you need 3 times as much O2 as you need. So, okay, very good. Any other questions on that one? Does it have a percent yield question that goes with that, or is that it on that slide? Okay, very good. What's the mass of my excess reactant? So what's excess mean? Left over or extra, right? Okay, so.
I need to find another word.
Nope, it's good. Leftover or extra. Okay, so my limiting reactant in this case was what? Oh, I didn't even finish answering this last question. What? My limiting reactant is O2. Okay. O2 is my limiting reactant. And then how many grams of carbon dioxide could be formed? It's only going to be that much, right? We forgot to finally answer that question. But I want to know how much leftover, how much excess of C2H4 is there. So what I need to do now to be able to solve this is I need to do another conversion from O2, from my limiting reactant, to C2H4. And that would tell me how much ethylene is needed to react all of that oxygen. Once I have that number, I can subtract it from my starting amount. Okay, so let's go ahead and go back to I'll go back to my next slide here. I'm going to convert from my limiting reactant to my excess reactant, essentially. Okay, so I'm going to go from 3.25 grams of O2. You're going to have to help me out with the mole ratio here because I moved slides.
3 to 1.
So 3 on the bottom?
Yeah.
Thank you.
Where are we going from O2
To C2H4. Because we're trying to figure out how much C2H4 is being used. That's what this chart is telling us.
Can you go from CO2 to H or C2H4?
Yes. I think so. Let's check the numbers and see if they match. It should, because if we're forming that much CO2 from that much oxygen that's being used, it should work out the same. Yep. So this is a mole of C2H4, 2 grams C2H4, and this is 28. Okay, so this T-chart doesn't tell us how much left over. It tells us how much is used. And that tells me I got about 0.948 grams C2H4 that is used up. Okay, so yep. I'm going to subtract. I started with 4.95 grams of C2H4. I'm going to subtract 0.948 or 0.95, and that leaves me with about 4 grams C2H4 left over. Does that kind of make sense? If your starting number was given in moles, you could stop your T-chart at moles and then just subtract in moles. You know what I'm saying? If your starting number was not given in grams, if it was given in moles. So you can kind of pay attention to what that starting amount is. Okay. Do we want to try another one of these, or do you want to keep moving? Let's keep moving. Okay, that's fine. We're going to do them on our homework too. Building and balance, we kind of did that yesterday. Do we feel pretty good about that still? Yeah. We're going to have a quiz on building and balancing next Tuesday. So you'll have to go build, balance, and solve. Okay, so you got to do all of those types of. Okay. Why is this not going? Is that it? Is that the last slide?
Yeah.
Oh, that's why it's not going. Okay. I'm